Now, with the top of the Atlas, this sort of blunt top, is where the bomb would be, encased in a protective copper nose cone that was supposed to withstand the heat of high-speed reentry back into the atmosphere. We'll get to more about reentry in a minute, but I want to also point out that the Atlas was a very unusual construction. It was made out of aluminum, and it was basically a metal balloon, which was only capable of standing upright when it was pressurized with fuel. The Atlas burned a very pure form of kerosene called RP-1, which was one of the major advances in rocket technology in the 1950s, switching from alcohol-water mixture to kerosene provided much more chemical energy and therefore much more thrust capability. And of course, every rocket has to have its own oxidizer to burn the fuel, since it's heading out of the atmosphere and doesn't have any means of obtaining oxygen at that point, has to carry its oxygen with it. So to serve as an oxidizer, there is a big tank on the Atlas of liquefied oxygen, liquid oxygen, which exists at a temperature of several hundred degrees below zero. And when mixed with the kerosene and put into the thrust chamber and ignited, produces all of that fire and all of that thrust. And again, an aluminum balloon, it could not stand on its own weight unless it was full of pressurized fuel. Now, the Atlas was under development in the 50s, and it took quite a while to develop the rocket. It was not ready for its first test flights until 1957 or 58, and so it was, however, ready in time when NASA was created and started thinking about how are we going to launch people into space. So, at that time, we knew the Russians had their big R-7 booster that had launched Sputnik, and both Sputnik 1 and Sputnik 2, remember that Sputnik 2 weighed a couple of thousand pounds, so we knew they had some pretty capable boosters. Our Atlas was not as powerful as the Soviets' R-7. It was capable of launching maybe 2,000 or 3,000 pounds into orbit. And so we had to think a little smaller than the Soviets did, and we'll see how that played out. But the real concern, as people started to think about designing a spacecraft for Mercury, was not how to get it into orbit. We were confident that the Atlas could take care of that. No, the problem was how, once you get the man into orbit, and he's now traveling 17,500 miles an hour in order to stay in orbit around the Earth, how do you get him back? That was the big technical question. Well, getting back meant re-entering the atmosphere at that very high speed of 17,500 miles per hour, and then using the atmosphere to slow down. Now, in the early 50s, as people like Wernher von Braun looked ahead to how you would actually carry out the dream of space travel, he and many other people assumed that the best way to design a spaceship to re-enter the atmosphere was to make it as pointed as possible, a kind of needle-nosed design. And you can see here a painting by Chesley Bonestell done in the early 50s of the third stage of von Braun's multi-stage spaceship re-entering the atmosphere, and it's glowing red hot because of the intense friction with the air as it is slamming back into the atmosphere. But the idea was that you would have this needle nose shape, and the wings would be sort of knife-edged in front, and you would build the ship out of some heat-resistant metal. And through the combination of making it as sharp as possible and as heat-resistant as possible, you would be able to withstand that re-entry heating and basically use those wings to glide to a landing on a runway. Well, that was the plan. Didn't quite work out that way. This is an actual wind tunnel simulation of a reentry into the Earth's atmosphere at very, very high speed using a needle-nosed shape. Now you can see this is kind of a photography called a shadowgraph. And you can see that you have a needle-nosed model of a missile, or it could be a spaceship. And it's in this very high-speed airflow in the wind tunnel. And the dark line that is coming off on either side from the tip of this pointed ship is the shock wave that is produced as the vehicle is going through this very intense high-speed airflow. Now that shock wave is very thin, and it doesn't provide much protection from that intense heat due to friction from that high-speed reentry. And in fact, when researchers in the early 50s started to make these kinds of tests, they found something very disconcerting, which was that the tips of the models actually got so hot that they began to melt. Now, obviously, this was not going to be a successful design for a nuclear warhead to re-enter the atmosphere safely, or anything else for that matter. So there remained the problem of how do you design a vehicle to make it through that intense heat, that heat of reentry, which was thousands of degrees hotter than the surface of the sun. Well, the fellow who made the breakthrough in the question of reentry was a brilliant aerodynamicist named Harvey Allen, who worked at the Ames Research Center of the National Advisory Committee on Aeronautics, the NACA. Now, the NACA was the precursor of NASA. It was the organization, it had actually been around since the 30s at least, and was a place where some of the cutting-edge research in aeronautics had been done in this country. And in 1958, the NACA would become NASA, National Aeronautics and Space Administration. But for now, in the early 50s, Harvey Allen was trying to come up with a way to design a warhead so that the eventual Atlas ICBM would be able to launch it, and it would be able to make it through the atmosphere and reach its target. And Allen had a brilliant insight. He realized that what you wanted to do was not be as sharp as possible, but to be blunt, and to slam into the atmosphere with a very blunt shape that would actually have a very different effect. What you see here is a test of a blunt body reentry, same kind of photography, shadowgraph photography in a wind tunnel, very high-speed airflow. But notice that now, with this very shallow, curved, blunt surface slamming into those air molecules, that what happens is that you create a very dense, thick shock wave, which is separated by some significant distance from the actual heat shield of the vehicle. And that shock wave acts as an insulating blanket to protect the spacecraft from most of the reentry heating. And there is some heat that makes it through that does reach the vehicle, but then what you would do is you would coat the vehicle with some kind of high temperature material that would be able to handle that residual heat. So the blunt body theory actually caused quite a stir. There were many experts who thought that it was a crazy idea. They were so in love with the idea of the needle-nosed concept, the shape, that they had a hard time seeing the validity of the blunt body, but eventually they came around. Actually, didn't take too terribly long as they started to make their own tests in wind tunnels